So for this exercise, we wish to find the relative extrema. So we want the local maximums and local minimums. I would begin by making a graph of this. If you want, you can make a table of values for the upper function and for the bottom function, where for the upper function, you pick values that respect the domain. That is, pick numbers that are less than or equal to 1 for that upper part of this graph. And if you want to make a table of values for the bottom function, you would pick x values that are greater than 1. So let me just graph the upper one sort of mentally. So let me pick 1 and plug it in here. If I plug 1 into this, I get back 3. So I go to 1, 1, 2, 3. Now, let me plug in 0, because 0 is part of this interval. So if I plug 0 in here, I get back 5. 1, 2, 3, 4, 5. Plug negative 1 in there, you get back 3. Plug negative 2, you get back negative 3, I do believe. And so on and so forth. And so now the graph of this, it's the portion of the parabola that is from 1 and before. That's what this means, right? It sort of cuts off this parabola at x equals 1 right there. Now, let's graph the bottom function. So I know that it says x is greater than 1, which means that here I would have a hole at x equals 1 because it's not equal to. Right there, you see that that's equality, which is why I filled this in. If that bar was not there, that would have been an open circle. So let's see. I know that it has to be greater than 1, but let me just pretend that I can use 1 itself, and I'll put a hole there. So plug 1 in there, you get back 3. So 1, 1, 2, 3. So I put a hole, but notice that you don't see it because it's actually filled in because these two parts sort of overlap. Sometimes that overlap happens, not all the time. It did here now. So pick more numbers that satisfy this inequality, like 2. You plug in 2, you get 4. You plug in 3, you get 5, and so on and so forth. This is what the function looks like. Now we can see here visually that we have a local or relative maximum of 5 at x equals 0. You see, the relative maximum value is 5. It occurs when x is 0, or if you want, at 0, 5. You see what I'm saying? Now we have a relative minimum of 3 at the location x equals 1. Because when x is 1, the y coordinate is 3. And if you were to zoom in there, you'd see that this point is less than or equal to all of the content that is immediately surrounding it. Similarly, this point, its y coordinate is greater than or equal to all of the points that are immediately surrounding it. You see, so there's sort of an interval surrounding that point where that's the king. And there's sort of an interval around this point where that's like the smallest, right? That's like the highest and that's like the smallest. So now look, could you have done this problem by taking the derivative of this piecewise function? I mean, I suppose so, but this is what the derivative would have been. I think it's clearer to make a graph if possible. And especially if it's a piecewise function. If this was like a polynomial or something, I probably would have done a derivative. But a piecewise function, I'm going to try to throw a graph. I'm going to try to put a graph and just analyze the graph. So here we are. I propose that these are the values. If these are incorrect, please let me know. But as is, let me submit that to you. And we want to know the points of inflection and the concavity. So we need the second derivative. Now let's see. The first derivative is obtained by hitting this with the product rule. So product rule is this. The first piece times the derivative of the second piece. Right? That's first derivative second. First derivative second. Yep. Plus the second piece times the derivative of the first piece. So that's the first derivative. If you want, we can clean this up a little bit. We can call this x over 2 square root x plus 5 plus square root x plus 5. Can this be simplified? Can we turn these two objects into one term? Yes, we can. Do you have to? No. And I just won't. Let's see. The second derivative, which is what we need, because the second derivative reveals points of inflection. The second derivative is the derivative of the first derivative. So let's take the derivative of this. First, focus on this term, the quotient rule. So let's go bottom derivative top. So the bottom times the derivative of the top, which is 1, bottom derivative top minus the top times, now let's take the derivative of the bottom. The derivative of that would be 2 times 1/2 x plus 5 to the negative 1/2. Close that. So let's see. Bottom derivative top, there, minus top derivative bottom, there, all over the bottom squared. Okay, this is the square of the denominator. Plus, and now the derivative of that would be 1/2 this here. Now look, if the goal was to submit to them the second derivative, then I would clean this up a lot, but that's not the goal. The goal is to find the points of inflection, which means we take the second derivative and we set it equal to 0. So let me do that, and I guess I'll do a little bit of cleaning, such as that knocks out. So let me jot down the second derivative, having simplified it just a little bit. So I'm thinking this here, I'm thinking something like this, and that there, over this here, plus this business here. So here is the second derivative, a little bit simplified. Let me take a look at this. Do I like this? Yes, I do. Now take the second derivative and set it equal to 0. So let's solve this equation and let's see what it tells us about the points of inflection. So subtract this to that side. And now I'm gonna multiply this denominator and drop it on this side. So let me go like this. I'll multiply both sides essentially. Multiply both sides by the denominator, which conveniently knocks this out. And it puts this on top of that. So here's what I have now. And now what I'll do is I'll multiply each term by square root x plus 5. Every term gets multiplied. Multiply this and this and this by square root x plus 5. Square root x plus 5, square root x plus 5. We have permission to do that. You're multiplying both sides by the same non-zero quantity. And so 2's there, that is this. These are gone, so it's minus x. These are gone, so it's negative 2x plus 5. And so we have x plus 10. I'll let you see the math there, like that. And what is this? This is x equals negative 20 over 3. Strange, but let's see. So I took the second derivative, set it equal to 0, and this is my solution. You know what? Look, that's bad, and I'll tell you why. Negative 20/3 is not even in the domain of the second derivative, because the second derivative, which can be seen essentially all of here, notice that we cannot square root a negative. So the domain is x is greater than or equal to negative 5. This is the domain of the second derivative. And this number is not part of this domain, right? So this is like from negative 5 to infinity. This is the domain of the second derivative. This number is not in here. So this is called an extraneous solution. And a lot of times extraneous solutions pop up whenever you start multiplying by variables, which is, a lot of times introduces bad things. Case in point, this number. So what I'm saying is the second derivative is never 0, because if it were ever 0, we would have found it, but there was no number. So the second derivative is never 0. So I'm inclined to believe that we have no points of inflection which implies that the original function f is either always concave up or always concave down. And you can test it by just plugging in a number into the second derivative. Plug any number that you want in the whole wide world, as long as it's part of the domain, plug it into the second derivative. Okay, how about 0? 0 is somewhere in there. If I plug 0 in here, I should get a positive quantity, which tells me that the original function is concave up on its domain. Now, is the domain -5 to infinity? Exclusive, I think that's how you say it, with the parenthesis, or is it with a bracket, inclusive? That is something else to ponder. So I'll let you think about how or which answer the computer prefers. But I think I've said enough. So let me know if you have any more questions and we can discuss this with further detail. And wait, wow, was the camera actually blurry throughout that entire process? I'm so sorry, I apologize. I should have double checked to make sure that this camera was focused on the material. But anyways, let me know if you have any more questions.